Hello again. What we're going to do now is the next section in chapter 5, the uniform random variable. We saw a glimpse of that in an example from 5.2 where f of x was 1 between 0 and 1 and 0 otherwise. You remember we also calculated the variance for that random variable, and along that we also looked at the expectation. Anyway, so some of you have seen this in a statistics class or elsewhere, and even if you haven't, that's okay. We'll look at a uniform random variable. Okay, now intuitively, what's a uniform random variable? So just take any interval, for example, 0 to 1. And just very broadly speaking, you can say you're just as likely to pick any one small region over another small region of the same width, okay? Or let's suppose you think of it as you're just going to throw a dart in this interval 0 to 1, and you're just as good or bad, and no one point is going to be hit with more frequency, or no one region is going to be hit with more frequency than another, okay? So how do we speak of this mathematically? And then we'll come back to what I was just speaking about. So suppose you have a random variable whose density is f of x is 1 when x is between 0 and 1 and 0 otherwise. Okay, OW standing for otherwise. So if you say if x has a probability density function given by this, then we say that x is uniformly distributed on the interval 0 to 1. Okay, so we've looked at this random variable in the example that we did in 5.2. We saw that its expectation was a half, which is exactly the midpoint of the interval 0, 1. We saw that the variance was 1 over 12, which we calculated by looking at expectation of x squared and subtracting expectation of x whole squared. Okay, this interval 0, 1 is just example. We could take any interval. So suppose you have an interval alpha beta, okay? And if you want to say x is uniform on the interval alpha beta, what do you have in that case? In that case, the density or the probability density function is given by, now what do you have? This is the interval alpha to beta. It's very similar to us having the interval 0 to 1 over here. And what do you have? The density will be 0 if x is not in the interval alpha to beta. Okay? And in the interval alpha to beta, well, you might want to say, well, let it be 1 in the interval alpha to beta. But if you put 1 and you integrate this function 1 over the interval alpha to beta, you will get beta minus alpha. But really, you do want that the integral from minus infinity to infinity of f of x dx, which in this case, because it's 0 over there, alpha to beta of f of x dx, you want this to be 1. So what do you need? In that case, you need that it's not just a constant 1, but it is 1 over beta minus alpha. Okay, so it's a constant on that interval, the density, and it's 0 outside of that. So here's alpha, here's beta, and the density is constant 0 outside of that. At the endpoints, it doesn't matter what you do because it's 1 point. And it's the function, the height is 1 over beta minus alpha on the interval alpha to beta. Okay, and you can check, well, since beta is bigger than alpha, this is a non-negative function. if you integrate f of x from negative infinity to infinity, you do get 1. Okay? And then if you pick any interval, how do you find the probability that x is in that interval? Well, if the interval is outside of alpha to beta, then the probability x is in that interval will be 0. And if the interval, let's say a to b, is in here, then how do you find what the probability of x being in a to b was? So let's suppose we have that a is bigger than alpha and b is less than beta and b is bigger than a. So suppose that you have this. Then the probability that x is in the interval a to b, what will it be? It'll be the integral from a to b of the density of x, right? And so that's the integral from a to b, 1 over beta minus alpha dx. So that is b minus a over beta minus alpha. So what do you have? Over here, you have that this is, if you look at it, it is the length of the interval a to b over the length of the interval alpha to beta. So you see the probability of x being in an interval, as long as that interval is in alpha to beta, it just depends on the length of the interval. It'll be the length divided by the entire length. So if you have two intervals of equal length in here, alpha to beta, gamma to delta, then the probability of being in a to b and gamma and delta, the probability of being a to b or in gamma to delta is going to be equal if the lengths of these two intervals are equal. Okay, so that's something to note for uniform random variable. And so you see, when you're like, suppose you're very bad at darts or something like that, and let's say all you're looking for is, or maybe you're playing the game with chuck the sack, I think, right? And let's say you're standing over here, okay, and you're chucking this little sack and it needs to be falling in that interval. Or maybe there's a goal of being in there, but you're just bad, you're just gonna throw it and it lands anywhere. And if you ask yourself what's the question, it's in that interval, well, it would just be the length of that interval over the entire length, assuming you always do throw it within the boundary that it needs to be. All right. Or you could think of bowling. You know, say you're bowling and you're a little kid and the gutters are blocked off, and so there's no gutters, they're blocked off, and you're bowling and the ball, you're just so bad or just so uniform that it could be anywhere in there. All right, so then you would have, if you pick any interval, what's the probability that the ball ends up there or there, it would just depend on the length of the interval. All right, and we have seen in this situation that the expectation of x, we didn't see it in this situation, we saw it when it was 0, 1. What's the expected value of x? Well, let's see, that'll be the integral from minus infinity to infinity of x times the density. Okay, so let's take a look. In this case, because the density is 0 outside of alpha to beta, so let's write it in the notation we have. So this is how you say x is uniform alpha to beta. Then the density would be 1 over beta minus alpha on the interval alpha to beta and 0 outside. So you have that. So 1 over beta minus alpha and x squared over 2 alpha to beta. All right. So let's write down, what is it? It'll be beta squared over 2 beta minus alpha squared over 2 beta minus alpha, or if you want, you can write it as beta squared minus alpha squared over 2 times beta minus alpha. Well, let's factor the numerator. That's beta minus alpha times beta plus alpha over 2 times beta minus alpha. These cancel. Beta is not equal to alpha, so that's not 0, so you can cancel it. So the answer is beta plus alpha over 2, or if you want, alpha plus beta over 2. So it is exactly the midpoint of the interval. Okay, and intuitively too, that's what you would expect, that the expectation of this random variable is exactly the midpoint. All right. So I'm always just following this standard formula for the expectations, x times f of x, and integrating it. All right, and how about the variance of x? Well, what's the variance of x going to be? It's the expectation of x squared minus the expectation of x whole squared. We already know this. Let's try and find the expectation of x squared. And expectation of x squared will be, just going through this again, integral from minus infinity to infinity, x squared times the density, which turns out to be, this is 0 outside of alpha to beta, so let's just integrate from alpha to beta, x squared 1 over beta minus alpha dx. And that will be 1 over beta minus alpha, x cubed over 3 evaluated from alpha to beta. Let's just make this clearer. So that will be beta cubed minus alpha cubed over 3 times beta minus alpha. And you remember your factorization for b cubed minus a cubed? It is b minus a times b squared plus ab plus a squared. So this will be beta minus alpha times beta squared plus alpha beta plus alpha squared over 3 times beta minus alpha. Once again, beta is not equal to alpha, so you can cancel that, and that's the expectation of x squared. Okay, so what's the variance of x? It will be exactly this. Beta squared over 3 plus alpha beta over 3 plus alpha squared over 3 minus, so that's the expectation of x squared, minus the expectation of x whole squared. Okay, and working this out, what do you have? You have beta squared over 3 plus alpha beta over 3 plus alpha squared over 3 minus alpha squared over 4. 2 alpha beta over 4. Okay, so when you have alpha squared plus 2 alpha beta plus beta squared over 4. Okay, so you have alpha beta minus alpha beta over 2 and minus beta squared over 4. Okay, so you'll have beta squared over 12 minus alpha beta over 6 plus alpha squared over 12. And that is exactly 1 over 12 beta squared minus 2 alpha beta plus alpha squared. So that is beta minus alpha whole squared over 12. And you remember in the situation when the interval was 0 to 1, we had 1 over 12. So that's 1 minus 0 over 12. So this is the variance of a uniform random variable. You know, we're going to look at many different continuous random variables too. So just as you might have done in the discrete case, it would be nice for you to make a table of the name of the random variable, a little description of the random variable, write down the probability density function. So you have the name, description, the probability density function. If you want, write down the cumulative distribution function, the expectation, and the variance. Okay, so for different random variables, start making a table of these, and the first one you can put for the continuous is uniform, we're going to look at normal, we're going to look at exponential, and so on. Okay? So that takes care of the variance of a uniform random variable. All right. So let's now go ahead and look at some examples, okay, where we're using this. Okay. The first example I'm going to look at is, okay, let's just first do a basic one, okay? Let's suppose x is uniform from 1 to 9, all right? And I'm going to ask you 3 questions. One is, what's the probability x bigger than or equal to 3? The other is, what's the probability x is between 2 and 4? And the other is, let's find the CDF of the random variable x. Okay, so this is something you should also do in general for A to B. Okay, if you have a random variable that's uniform A to B, you should be able to find the CDF of it. Okay, so let's go through this. What is the probability of x bigger than or equal to 3? Okay, well, first let's look at what is the PDF of the random variable x. Well, it is x is uniform on the interval 1 to 9. All right, so what do you have? The density is 1 over 9 minus 1 on the interval 1 to 9 and 0 otherwise. So this is 1/8 on the interval 1 to 9 and 0 otherwise. Okay, so now we can answer this question. Was the probability x bigger than or equal to 3? All right, what do we have to do? We have to integrate from 3 to infinity the density of x. Okay, well, the density of x is 0 beyond 9 and to the left of 1, but we already are just going from, you have going from 3 to infinity. From the density, though, is only non-zero over here. You want to go from 3 to infinity, so you just integrate from 3 to 9, the density 1/8 dx. Okay, and working this out, it's going to be 9 minus 3 over 8, so 6 over 8 or 3/4. All right, so that's the probability x is bigger than or equal to 3. And then ask the question, what's the probability x is between 2 and 4? Okay, same thing. Integrate from 2 to 4 the density of x, and the density is non-zero on 2 to 4, so you don't need to do any adjustments. It's just 2 to 4, 1/8 dx, so it's 4 minus 2 over 8 or 2 over 8 or 1/4. All right. Okay. And lastly, let's find the CDF of x. In fact, let's just do this in generality. Okay. So let's suppose x is uniform alpha to beta. Okay. And we want to find the CDF of x. Okay. So I find it very useful to do this. Think about this for a second. What is the range of x? Okay, so the range of x is alpha to beta. X is going to be in the interval alpha to beta with probability 1. All right, so the range of x is alpha to beta. All right, so you can just think of this very loosely, that it's never less than alpha and it's never bigger than beta, or it's less than alpha with probability 0, it's bigger than beta with probability 0. All right, so it helps to just think of it as, okay, it's never less than alpha, it's never bigger than beta, and the range of the random variable is alpha to beta with probability 1. Okay, so what's the CDF? So we want to find the CDF, so f of a. That's the probability x is less than or equal to a. Okay, so let's draw this. Let's say you have alpha and beta. So let's suppose in case 1, A is less than alpha. Okay, so what's the probability x is less than A? Well, you know x is always between alpha and beta. So the probability x is less than a number less than alpha is 0. So this probability is 0 if A is less than alpha. Okay, and let's suppose now in case 3, A is bigger than beta. What's the probability x is less than A? So what can you tell me? What's the probability x is less than A? You know x is always between alpha and beta. So if A is bigger than beta, the probability x is less than A, this will be 1. Okay, and lastly, this is the most complex situation. Let's pick an A in the interval alpha to beta. Now, what's the probability x is less than A here? So what's the probability you're in that interval? That's the same as the probability that you're in this interval because you're never less than alpha. So this will be the same as the probability that x is between A and alpha, if A is between alpha and beta, right? And what is this probability? We've already seen this is the length of this interval divided by the entire length. So it's A minus alpha over beta minus alpha if alpha is between A and B. All right? So let's write this result down all together. F of A is 0 if A is less than alpha. It is A minus alpha over beta minus alpha if alpha is between, if A is between alpha and beta. And it is 1 if A is bigger than beta. And you can put equality any one of those places that you want. Okay, so this is the CDF of a uniform random variable. Okay, and you can see when you differentiate it, you will get the appropriate PDF. The same 1 over beta minus alpha over there, 0 here and 0 here. Okay, so in our situation, you have that if x is uniform 1, 9, then what is the CDF of x? Well, it will be 0 if A is less than 1. It'll be 1 if A is bigger than or equal to 9. Okay, and what is it between 9 and 1? It will be A minus 1 over 9 minus 1, 8, if A is between 9 and 1. So that's the CDF of a uniform 1, 9 random variable. All right, so I hope that made sense for the general case as well as this particular case. And of course, in this particular case, you didn't need to go through the general case. You could have just done it directly. Okay. And don't forget, for CDF, you think of everything you've accumulated. Think of CDF as the cumulative distribution function. So everything you've accumulated from negative infinity to that point. How much density have you picked up? Or what's the probability of being in there? Remember that molten gold pot that put all that molten gold till that pot. And if you vacuum it up, how much have you vacuumed up till that point? So you have to collect all the probabilities till that point. So very loosely speaking, that's what you need to do. So you integrate the probabilities or the density function till that point. Okay. All right. So that's an example for a particular case with numbers over here. And now let's just look at another example. This is a example from the book. And it is example 3C from the book. Okay, so page 199 in the 10th edition. I will read it, though I won't write the whole problem down. Buses arrive at a specified stop at 15-minute intervals starting at 7 a.m. Okay, so that is the bus arrives at 7, at 7:15, at 7:30, at 7:45, and you can say 8 o'clock and 8:15 and so on. Okay, so starting at 7 a.m. buses arrive every 15 minutes. Okay, if a passenger arrives at the stop at a time that's uniformly distributed between 7 and 7:30. So what do you know? The passenger arrives at a time that's uniform. So arrival time of passenger is uniformly distributed if from 7 to 7:30. All right? What you have to answer is find the probability that he waits less than 5 minutes for the bus, or find the probability that he waits more than 10 minutes for the bus. Okay? All right. So this is the scenario. Now, a lot of you might want to write. So what do we have to do? We look at this problem and we ask ourselves, what is the question asking? The question asks about how long he waits, his waiting time. Well, if you create a random variable, which is let t be the amount of time he waits, then that's going to be a very complicated scenario, because the waiting time, well, where t is, it would depend on where your t is and which bus the person's gonna catch. So instead of that, you don't let t be the amount of time he waits. What do you think you should let t be? You should let t be the arrival time of the passenger. So you might want to say, well, let t be the arrival time of a passenger, so t is uniform from 7 to 7:30. Well, that's kind of weird, because random variables have a range as numbers, and here you're talking about 7 to 7:30. So we need to fix that. We can't say that t is the arrival time of a passenger. Instead, what you need to do is manipulate it a bit and say, let t be the arrival time of the passenger after 7 o'clock. Okay? Okay, so what do you know about t? The arrival time is uniformly distributed between 7 and 7:30. So you know that t is uniform from 0 to 30. Does that make sense? Because the passenger is going to arrive anytime from 7 to 7:30, you can call t, which is arrival time after 7 o'clock, as a random variable that's uniformly distributed from 0 to 30. All right. And now we want to ask the probability that passenger waits less than 5 minutes. Okay, so go back to this number line or the timeline and ask yourself, when will he have to wait less than 5 minutes? Okay, so the bus certainly arrives at those fixed times. That's fixed. The bus arrives at 7, 7:15, 7:30, 7:45, 8, 8:15, and so on. The passenger always just arrives between 7 and 7:30. Okay? So, and you assume that this is uniform 0 to 30, so the passenger will never get the 7 o'clock bus. That's not happening. So you want to know what's the probability that he waits less than 5 minutes. What will make him wait less than 5 minutes? Well, he's going to catch this bus or that bus. So if he arrives after 7:10 or 7:10 or later, or if he arrives at 7:25 or later, then he's going to wait less than 5 minutes, right? So that's the question you ask. So this is the same as probability. So if he arrives anytime 7:10 on, then he's going to get the 7:15 bus. 7:10 to 7:15, he'll get the 7:15 bus. If he arrives from 7:25 to 7:30, he'll get the 7:30 bus. If he arrives after 7:15, he'll have to get the 7:30 bus. But if he wants to wait less than 5 minutes, you see, he has to arrive in one of those two intervals. Okay? So this probability is that T is in 10 to 15 union 25 to 30. Does that make sense? Okay. This is what will make him have to wait less than 5 minutes. And probability of T being in those two intervals, well, that's a disjoint union. So this is the probability T is in 10 to 15 plus the probability T is in 25 to 30, correct? It's a union of disjoint intervals. So the probability of T being in that is the sum of the probabilities. So you can say 10 less than T less than 15 plus the probability 25 less than T less than 30. Okay. What's this probability? It's going to be the length of the interval, 15 minus 10 over the distribution of T. T is uniform 0 to 30, so that's 30 minus 0 plus 30 minus 25 over 30 minus 0. Okay, so that's 5 over 30 plus 5 over 30. That is 10 over 30, and 1/3 is the probability that he has to wait less than 5 minutes. And if you wanted, you could have actually done this integral from 10 to 15 of the density plus integral from 25 to 30 of the density. Okay, and also you get the same 1/3 answer. Okay? So I hope this makes sense. To me, drawing the line is what makes it clearest. Okay, so now in part B, you ask, what's the probability that he waits more than 10 minutes? Okay, so now think about this. The passenger will arrive certainly in that time, okay? So 7 o'clock, 7:15, 7:30. I mean, in this interval, okay? That's when the person arrives. So what will make him wait more than 10 minutes? Well, take a look. So if you go to 5, if the passenger arrives anytime in that interval, he'll be waiting less than 10 minutes. But if he arrives in that interval, well, he can't get that bus no matter what. He's going to have to wait more than 10 minutes to get the 7:15 bus. Or if he arrives from 7:15 to 7:20, if he arrives anywhere in that interval, then he's going to have to wait more than 10 minutes to get this bus. Okay? So this you can write down as the probability, same as before. T is between 0 and 5 plus the probability that T is between 20 and 15 or 15 and 20. And same thing, you'll have 5 over 30 plus 5 over 30, 10 over 30, and you can do the integration also. Or you can do the integration and you get the same thing, that the probability that he waits more than 10 minutes is also 1/3. And well, what's remaining? Less than 5 minutes, more than 10 minutes. So the probability he waits between 5 and 10 minutes will be 1 minus 1/3 plus 1/3, also 1/3. Just an observation. They're not asking you that in this question. Okay? So that's all for uniform random variables. And I suggest that you get some practice looking at functions of random variables. So for example, here, let me give you an example. Suppose that x is uniform from 1 to 9. Okay, let's just take that example we were looking at. And let's suppose you're looking at the function y, which is equal to x squared. Okay, so let's suppose you're a pizza maker and you're just very bad at rolling out the dough. And the radius of the pie you make is uniformly distributed between, this is not realistic, of course, 1 foot and 9 feet. And you're asking yourself, well, what is the distribution of the area of the pie? Okay, well, that would be pi times r square, and you could drop the pi and put it back in later because it's just a constant, or you could ask about the distribution of the square of the radius, which really essentially is like the area with the pi factored out. Okay, so just a little worded example to go along with this uniform 0, 1. Okay, so suppose x is uniform 1, 9, sorry. Suppose x is a random variable that's uniformly distributed between 1 and 9. And the random variable y equals x squared. Okay, and I'm going to ask you 2 questions about y. Find the probability density function of y, and 2, find the expectation of pi times y. Okay, just a little something, because this would be the expectation of the area of the pie, not the pie, the pizza pie. Okay, all right, so we want to find the PDF of y. All right, so what do we want? We want f sub y of little y. Okay, so when we have more than one random variable floating around, it's good to write down the subscript of the random variable that you're talking about. Okay, well, how do we find out the probability density function? What we do use is this is the derivative of the cumulative distribution function. Remember I said that when you want to find the probability density function of a random variable, you do it via the CDF of y. Okay, so let's look at the CDF of y. So f sub y of y is the probability that the random variable y is less than or equal to y. Okay, all right, so what do we do now? We don't just jump in and start doing calculations. What we need to do when we're looking at CDF or PDF or anything, first, let's stop and ask ourselves, what is the range of y? Okay, well, you know, x is uniform 1, 9. So I'm going to say it in 2 ways. With probability 1, x is between 1 and 9, which is equivalent to saying with probability 0, x is less than 0 or bigger than 9. Or very loosely speaking, you can say x is always between 1 and 9. Okay, but saying x is between 1 and 9 with probability 1 is the more mathematically correct way of saying it. Okay, so if x is uniform between 1 and 9, you can say that x is bigger than 1 and less than 9 always. So what do you have x squared? You firstly don't jump and say x squared is uniform 1 to 81. You can't say that. But what you can say is x squared is going to be between 1 squared and 9 squared. So with probability 1, x squared is going to be between 1 squared and 9 squared. So you can say that the range of y is the set 1 to 81. Okay, it's that interval. All right, it's the interval 1 to 81. Okay, but you can't say uniform. Don't make that mistake. That's a very, very common error that I have seen. If somebody sees that a random variable is uniform, then a function of it is uniform on the new interval. Well, that's simply not true. Unless you have a linear function, it's simply not true. Okay, so let's go back to this, the CDF of y, and try and figure out what the CDF of y is. Okay, well, you know that the random variable y is going to be between 1 and 81. All right, so the probability that y, so here's 1 and here's 81. So let's suppose you pick a little y to the left of 1. What's the probability y is less than that? Well, you know y is always between 1 and 81. So this is 0 if y is less than 1. Okay? And then pick a number to the right of 81. Okay, so here's 1, here's case 3. And what's the probability y is less than this? Well, the random variable y less than any number bigger than 81, that's going to be 1 because it's always between 1 and 81. So if y is bigger than 81 with probability 1, random variable capital Y is less than or equal to y that's 1. How about in here? Well, now we're going to put in y equals x squared, and we're going to have to do some more work. Okay? Here, you can just put strictly. All right. So let's look at the situation of what happens when you pick a number in there. Okay. So f sub y, so let y be between 81 and 1. F sub y of little y. That's the probability, the random variable y less than or equal to little y. That's the probability x squared less than or equal to little y. Well, what do you have? If x squared is less than or equal to y, what do you normally say? Normally you would say that x is between square root y and negative square root y, right? Okay, but x is never negative. In fact, x, so here you have 1, here's 81, okay, and suppose you have y, somewhere you have square root y, and let's say that's negative square root y, and here's your 0. You want to find the probability x is in there. Well, x is never less than 1, so essentially you're asking what's the probability x is between 1 and square root y, right? So you rewrite this because x is never less than 1. 1 less than x less than square root y. Okay? And what is this? If you want, it's integral 1 to square root y of the density of x 1 over 8 dx, and that is going to be square root y minus 1 over 8. Okay, so the CDF of y is square root y minus 1 over 8. If y is between 81 and 1, it is 0 if y is less than 1, and it is 1 if y is bigger than 81. Okay, so I'm just going to put it all together and write it down. So f sub y of y, that's the CDF of the random variable y, is equal to 0 if y is less than 1. Square root y minus 1 over 8 if y is between 0 and 81. And it is 1 if y is bigger than or equal to 81. Okay, so that's the CDF of y. All right, and how do we find the probability density function of y? Well, we will just differentiate the CDF. Okay, differentiating 0, you get 0. Differentiating 1, you get 0. And differentiating in there, you have d dy of y to the 1/2 minus 1 over 81. Okay, let's do that. That's 1/2 y to the negative 1/2. Okay, so it's 1 over 162 square root y. If y is between 81 and 0, and 0 otherwise. Okay, so that is the probability density function for this random variable y. You see, it wasn't just as simple as let me just square the ends of the interval and it's uniform on that. That's certainly not uniform. So that is the probability density function of y. And the other thing we're asked is what's the expectation of pi y? Well, the expectation of pi y, you could do it in two different ways. One way is just integrate from minus infinity to infinity pi little y times the density of y. Or you could do it as expectation of pi x squared, which is integrate from minus infinity to infinity pi x squared times the density of x. Either ways, it's fine. And if you want, let's just do it in this way. You have 1 to 9 pi x squared. What's the density? 1 over 9 minus 1, 1 over 8 dx. So pi over 8 sits outside, x cubed over 3, going from 1 to 9. All right. So you have pi over 8, 9 cubed over 3 minus 1/3. Okay. 9 cubed is 729, so 728 times pi over 24. And I'm sure that stuff cancels from here. Okay, so you have 8 times 3 and 8 times 91, and it's just 91 pi over 3. Okay, so that's the expected area of a pizza pie where the radius is uniform 1, 9. Okay, and of course you could do it in this way also by using this density that you found. But if in a problem you were not asked to find the probability density function of y, then you could just directly just use the expectation of g of x, use this form and just apply this formula and find the expectation in this way instead of going via the PDF. Okay, well, that's the end of 5.3 and uniform random variables. The next section we're going to look at is normal random variables. And as usual, please email any questions you have. They're going to be gathered and collected in small batches or appropriate batches. And I'll send the answers of entire batches together. All right. That's the end of this. Okay, bye.